Good. Let's look at one specific example. So handwritten digits. So this is image processing. The task here is you're trying to help the post office, right? And I guess this particular one is the U.S. post office, right? So the U.S. addresses have postal codes, and they're completely numeric. So it's just a sequence of 5 numbers. And when you send a letter through a post, those digits, those postal codes, they actually get processed automatically by a machine. So there's a machine that's going to look at the envelope, read, and try to read off the postal code. So it's a particular kind of handwriting recognition, but what makes it difficult is usually when you do handwriting recognition, your code is on the same device where the person is doing a handwriting, right? So if you're wondering why handwriting recognition on your tablet or on your phone is so good, it's because it is computing the right characters as you type them. It has access to lots of data other than pixels. So it knows where the pen is, it knows how the stroke is moving, it knows how much pressure you're putting on the pen. And all of that information is fed into the character recognizer. Here, the problem is harder because you cannot put a computing device on a paper envelope, on every paper envelope. So what comes in is just a bitmap. It's just a handwritten bitmap. All of that additional information is not present. So that's what makes the problem challenging. And if you look at it, you actually see lots and lots of variation in the way that different numbers are drawn. So just look at the 2s, look at that 2. You can barely recognize that. Now we as humans recognize those digits perfectly, but it's actually pretty hard for a machine to do it well. So what are the possible representations that we could use for that, right? So one representation that's actually used surprisingly often and makes sense. Once you've boxed each digit, once you've identified a bounding box, so say you end up with a 20 by 20, you scan it, maybe you end up with a 20 by 20 bitmap. Each pixel is a gray level, so it's a real number, maybe a number between 0 and 255 or something else. It's the amount of blackness. So one representation that you can use for this data is you can actually represent each pixel as its own attribute. It's particularly simple, and it has many problems, but it does work. So if we have a 20 by 20 bitmap, this means that we have 400 attributes. And what kind of attributes are they? Well, to start with, they are numeric attributes because each pixel has a shade of gray associated with it. But then you could actually do you could do interesting things with it, right? So you could, for example, convert it to black and white. Right? That would simplify it a lot. So you just put a threshold on it and look at where the black is. You put a 1. Where the white is, you put a 0. So this way you would still have 400 attributes, but now they'd be binary. So it seems natural to do, right? After all, you're recognizing a digit. There shouldn't be shades of gray there, and it's a lot more space efficient. Now it turns out that doing that is actually a really bad idea. So if you try to threshold it and convert it to 0s and 1s, your accuracy is going to suffer quite a bit. And strangely, the opposite helps. So if you take a digit and blur it, right, just make it fuzzier, that seems to help the learning algorithms. Any idea why?